C.v.Raman once said, "Ask the right questions, and nature will open the doors to her secrets." Physicists observe nature and its beauty very carefully, and if they found something interesting, then they must try to find the reason behind that. Here is another story about an Indian man who won the Nobel Prize in Physics after his discovery, which idea came in his mind from the beautiful scenery of Mother Nature. 𝗘𝗕ncia𝗕𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏 who carried out groundbreaking work in the field of light scattering, which earned him the 1930 Nobel Prize for Physics. How did Raman discover the Raman effect? In 1921, Raman had traveled to Europe from his home in Calcutta to attend the Congress of Universities at Oxford. But it was his trip that would lead Raman to change history. During his sea voyage, he observed the blue color of the Mediterranean and wondered about the origin of this beautiful phenomenon. Raman was aware of Lord Rayleigh's explanation that the color of the sea was due to the reflection of the blue sky, but he did not accept it. So, with a polarizing nickel quartz prism that he carried in his pocket, he proceeded to demonstrate Rayleigh's explanation to be false. He quenched the surface reflection of the sky on the sea surface and noted that the blue color of the sea was unattenuated. With a diffraction grating, he showed that the maximum spectral intensity was different for the blue sky and the blue sea. During this voyage, Raman sent 2 papers attached to the journal Nature positing that the color of the sea was due to light scattering by the water molecules, a phenomenon he called molecular diffraction. Thus began Raman's new research obsession, the molecular basis of light scattering. Back home in India, Raman and his students observed the frequency shift of scattered light. They knew the phenomena was not Rayleigh's scattering, since that type of scattering did not produce a frequency shift. However, they needed to exclude the possibility that minute traces of fluorescence were causing the shift. To do this, they purified the liquids multiple times. When the phenomenon remained, they concluded that it was not due to fluorescence. By 1925, Raman had observed the frequency-shifted scattered light in more than 50 liquids, and, by 1927, he had noticed that the scattered light was polarized. He described the phenomenon, which he called modified scattering, in a paper in Nature. Later it would be called the Raman effect. What is the Raman effect? Raman effect changes in the wavelength of light that occurs when a light beam is deflected by molecules. When a beam of light traverses a dust-free, transparent sample of a chemical compound, a small fraction of the light emerges in directions other than that of the incident beam. Most of this scattered light is of unchanged wavelength. A small part, however, has wavelengths different from that of the incident light. Its presence is a result of the Raman effect. If the scattered light in a direction perpendicular to the incident beam is spectrographed, it is found not only to contain a line corresponding to the frequency of incident light, but also a pattern of relatively weak lines on the low-frequency side of the incident light and a similar pattern of still more weak lines on the high-frequency side. Quantum theory of Raman effect. The occurrence of Raman scattering may be most easily understood by considering radiation of frequency nu as consisting of a stream of particles called photons having energy h nu. Photons can be imagined to undergo collisions with molecules and, if the collision is perfectly elastic, they will be deflected unchanged. This gives rise to Rayleigh scattering. But if the collision is inelastic, then there can occur an exchange of energy between molecule and photons. This exchange of energy can be of 2 types. The molecule before the collision occupies a lower vibrational or rotational energy level, and after the emission of the photon, it may be present in any one of the higher energy levels as permitted by selection rule. In this case, the molecule gains energy equivalent to the energy difference between the 2 involved levels. The energy is provided by the photon and hence its energy is decreased, and thus a Raman line on the low frequency side is observed. Such a Raman line is called Stokes line. If the molecule before the collision occupies one of the higher vibrational or rotational energy level, and after the emission of the photon may be present in any one of the lower energy level as permitted by the selection rule. In this case, the molecule loses an energy equivalent to the energy difference between the 2 involved levels. This energy is gained by a photon and hence its energy is increased, and thus a Raman line on the high frequency side is observed. Such a Raman line is called an anti-Stokes line. Raman effect has much application in different fields of science like biology, chemical science, semiconductor, carbon materials, pharmaceuticals and cosmetics, etc. If you like this video, please share it and don't forget to subscribe to this channel. Only 2% of watchers are subscribers, 98% are not. So please subscribe and help to grow this channel.